we need some notion called the enclosures. This was first proposed in a SIMO 2020 paper, but this paper studied some foreign key join queries. So this is not the same class of queries we are interested in today. But the notion is very interesting there. So it considers an update sequence. So each tuple here defines a lifespan interval. Okay. So for this tuple, T plus is the time step. Tuple T is inserted, and the T minus is the time step. This tuple will be deleted. Okay. So what's the enclosure list of this tuple? It's defined as the maximum number of disjoint lifespans contained in this lifespan tuple. Lifespan interval. Okay. Then what's the enclosure list of the update sequence? If you look at this part, this is the average, just the average of the enclosure list of all the tuples in update sequence. Okay, and we require that it should be at least one. Okay. They show the for this first in first out update sequence. Okay, the enclosure list is just one. It's very low. And they show the result that for the foreign key acyclic query, it can be updated in lambda s time for any update sequence with enclosure list lambda s.
So Xiao, what is S in lambda S?
S is the update sequence. We give a specific update sequence.
Yeah. So what is the form of S, Xiao? Is it tuples and the time when it is inserted, so twice the number of tuples?
You can just interpret it as the tuple and the lifespan interval. So updates you can interpret as the insertion or deletion, the timestamp, and which tuple for which relation. Yeah. And then if we look at
so for the picture here, does every tuple have 0 enclosed?
Exactly. Yeah. So we just for C required to be at least 1.
And then finally, the big O is with respect to the entire sequence, yeah?
Entire sequence, yeah.
And what is foreign key acyclic query?
Sorry, what did you say? 0? What is 0?
There's no disjoint lifespan completely inside this.
It's properly contained, like its own lifespan is always contained. So
completely contained. Yeah. Yeah, so it's 0. Okay, next question is what is the foreign key? Yeah, you can read the paper because they assume, for primary key table and the foreign key exists in a query. So this is an easy class of query because the output size is always linear. Yeah, so there's not many challenges in update settings, but it still requires some techniques there. Okay, so this first in first out sequence has a very low enclosure list, but the question is this notion of enclosure list good enough? Okay, yeah.
One more question. So every update has a lifespan associated with it?
Yeah. Okay. Question. Yeah.
So just in the problem framing, I think this is the first time we've seen the cost metric be over an update sequence, right? Previously, it was per query or per update kinds of analyses.
Yeah.
Is there any connection between the average case of the per update analysis and what we're now doing on the whole batch analysis?
I don't know.
Okay.
So that might be a good question for group discussion. Okay, so if we just consider this query, and we can show that even under the first in first out update sequence, it still requires routine update time under some the OUMV conjecture. So this means that the first in first out sequence has very low enclosure list and their definition, but it still cannot capture the hardness of the update for this query. So I assume that you all know about the OUMV conjecture. So So I will skip this part and show some idea why this query is hard and the first in, first out update sequence. Okay.
So sorry, are you saying that the result is wrong?
No, I just said that their notion may not be enough to capture the hardness. They didn't consider conjunctive query. They only considered the foreign key acyclic query. Yeah, they didn't say anything about the.
So you're saying that their result fails if you have an acyclic query, which is not a foreign key acyclic query.
Yeah, I said that their notion is not good enough to capture the hardness for conjunctive queries without foreign key. Yeah.
But still acyclic or not acyclic?
Acyclic. Actually, we just focus on free convex query, conjunctive query. Yeah. So if you are familiar with something with the OUMV conjecture, so the common approach to show the reduction is that we want some relation to simulate the matrix, so and then use some the other relation to simulate the vectors. But the insertion to this matrix will be insertion only. It will insert at the initial point, and then the vectors will be inserted and deleted. Okay, then you want to do the OUMV reduction. But here we only have first in, first out update sequence. How to do that? The idea is that we use this R1 and R5 as the indicator. Okay, so first we insert some integer like 1, 2 into the R1 and R5.
Xiao, what are you trying to prove? What is the claim that you're trying to prove?
Oh, yeah. The proof is that there exists any data structure for this query for supporting constant delay enumeration requires root and update time over first in, first out sequence. The how to encode the OUMV here. So same idea, we still want to use the middle relation R3 to encode the matrix. Okay. And for R2, we use to encode the vector U and R4 to encode the vector V here. But we need another indicator information here. Yeah. So in the first time, they are both 1. Then at this time, we can show that Q is not empty if and only if this is true. Then we just delete 1 from R1 and R5. Okay. At this time, okay, for this time point, we for the U2 and the V2, we further insert the tuples, okay, to R2 and R4 separately. But this time, those tuples have an indicator 2 here. So what does this mean? So all these tuples encoding U1, V1, U2, V2 exist in the database, but there is no corresponding indicator tuples in R1 and R5. So we conceptually deleted them from the database already because they won't contribute to the join result. Okay. At this time, Q is not empty if and only if this product is true. So the high-level idea is that we couldn't explicitly delete tuples here, but we can use the join information, right, to filter, to simulate this deletion process. Any question?
So that's why you need the path to be
Yeah.
like free, right?
Yeah, exactly.
Shorter, you couldn't see.
Exactly. Yeah, we use the R1 and R5 to simulate the deletion in R2 and R4.
I missed the point of why can't we delete directly from R2 and R4?
Because this is the first in, first out sequence.
I see.
Yes. If, for example, if we want all the tuples exist in M, we just insert them there, right? We won't delete them. But if we want to simulate OUMV, we need to, insert some tuples for U1, V1, and then delete them, and then insert U2, V2. But this is not first in, first out anymore.
Yeah. And you want the first in, first out sequence like to show that this is not hard under the previous definition?
No, previous definition does not say anything about the conjunctive query. I just want to say the previous notion is not enough to capture. Yeah, exactly. Okay, so you can also have some similar analysis here to show that if we want constant delay, then one has to pay at least the root and update time. Okay. So we need more complicated notion of enclosure list by exploring the query structure. So this notion is called the join tree-based enclosure. Okay. Similarly, we have an update sequence, but now we need a generalized join tree. And instead of just the lifespan of the tuples, we are interested in the effective lifespan of the tuples in the join tree. So what does the effective lifespan? So suppose this is a tuple T we are interested. There are two effective lifespans. The first one is that we only consider the first deletion of tuples, okay, from the descendant node of this relation. Okay. And this one is symmetrically defined at this one. Okay. So for this one, we consider this is the effective lifespan of T, and when we consider this, we can see the last insertion of some tuples from the descendant node of this subtree. Yeah. So in some sense, we just shrink the lifespan of the tuple. Okay. Now the join tree-based enclosure list for one tuple is now defined as still the maximum number of the effective lifespans that are contained in this one, but we only consider tuples from the descendant node of this relation. The intuition is that only the updates in the descendant node will change the status of this tuple. Okay. And similarly, the enclosure list of this whole update sequence is defined as the average enclosure list of tuples in the update sequence.
Excuse me?
Yep.
But this is now dependent on a particular choice of a join tree.
Yes, it depends. Exactly.
Can you compute efficiently this lambda st if you would have to go over all possible join trees?
Yeah, so this definition depends on the join tree. We just choose one join tree, you will have the enclosure list of update sequence. If you have another join tree, you may get another enclosure list. So the question is, interesting question in practice is, can you find the best join tree? Yeah.
But this
We
is
don't
not
know.
investigated.
Yeah, this is not investigated, and yeah, we can discuss how to do that. There are some heuristic there, but not so very formal, formal proof there. So let's revisit the example we just have, okay, for this query. If we look at the effective lifespan, so for this tuple, we consider the first decision. So you can imagine there are some gap here. So the first deletion will become, so the effective lifespan will just degenerate to a very, very small interval there, okay? So these are the effective interval of the tuples. And for this join tree, all those tuples have the enclosure list as 0, but for tuples from R3, for this R3, the effective lifespan, disjoint effective lifespan is essentially linear because you can just choose all those effective lifespans and they are all disjoint. Yeah, so that's why this query and this update sequence will have enclosure lists as large as root n. So this is not just the one by the previous notion of enclosure list.
I'm confused why we don't have to worry about multiple derivations.
Sorry.
I'm confused why we don't need to think about multiple derivations. It feels like, at least from the picture, that if I lose any one dependent tuple, then I know I don't exist anymore.
Yeah.
But with projection and so on, isn't it possible for me to have many derivations and there's like a disjunctive version of this picture or something that I'm not seeing?
Yes. I think I will have an example for joint projection
Okay, 'cause
first, but for this specific one, we're just interested in full joint results.
okay,
Yeah,
Right.
that's let's talk about this later. Okay, yeah.
limitation. Right.
Okay, so next question is this joint tree-based enclosure list good enough? At least for the algorithm data structure I just presented, yeah. For any free class query, the data structure built on a specific generalized join tree can be updated in lambda st amortized time over update sequence with this enclosure list, yeah. At the same time, we find one query such that it requires at least the lambda update time over update sequence with enclosure list assumed OMV conjecture. I didn't talk about the join tree here because for this simple query, we can just have these two generalized join tree. But we don't know whether lambda is good enough to capture all the queries. So this is still an interesting question to ask. So what properties, what of the update sequence we need to can exactly capture the hardness? Okay. Okay, I will just skip the lower bound for this part. For this part, it's similar. We just okay. So there's some picture I want to show. So we are interested in constant delay, and we want to ask a data structure that can be built in linear preprocessing time and updated in constant amortized time. If we don't have any restriction on the update sequence, then we know the query can have such a data structure if and only if it has a height one generalized join tree or it is Q hierarchical. Okay. But for other queries, we might have some restriction on the update sequence. For example, if the update sequence is first in, first out, we require that the query has a height 2 generalized join tree. And you can check the good exercise, you can check that the enclosure list is 1. Yeah. And if we want to have some result for all free class query, then we need to require that the update sequence should be insertion only or deletion only. Yeah. So when you have more restriction on the update sequence, then we can do better. Yeah. But yeah, I know there are some gap between those class of update sequence. So this is also an interesting question to explore. I think as an independent interest question is, can you have some nice structure characterization of conjunctive queries with height 2 generalized join tree? Because for the height 1 generalized join tree, we have a very nice Q hierarchical property. But how about for queries with height 2 generalized join tree? Can you say something about the structure there? And this also gives us some guidance for practical update sequence. Yeah, just the question asked. If we know some relations is never updated, for example, country, those information, or if you have some relation which is frequently updated, such as the order information, or some relations is not that frequently updated, but can update it at some time, for example, the customer information, then how to find such a good generalized join tree to do the update. There are some other interesting questions. Can we have more fine-grained analysis of the update sequence? Just consider this simple example. We have information when all of the updates are arbitrary, all of them are first in, first out, all of them are insertion only. Then more fine-grained question is if some updates are arbitrary, some are insertion only, can you still determine, find out the hardness or find the efficient data structure? Yeah, you can ask a lot of combination of those questions. But yeah, I'm not sure whether this is a good way to ask question in this way, but you can just define the fine-grained analysis, yeah, if you for your interest. Now I will talk some lower bounds. So these are the existing results for non-free connects query over insertion-only update sequence, and also non-Q hierarchical over arbitrary update sequence. So we are still missing the part for conjunctive queries without hide to generalize the join tree. We already showed this in our previous example, and this is another example we couldn't do it efficiently. This with the projection here. Okay, yeah. Natural question is: are these two? Can we extend the harness result to all conjunctive query with frequentless conjunctive queries without a hide to generalize the join tree? Yeah. I have some. Okay, also it's similar. We use the indicator, okay, to simulate the deletion. Yeah. First input down. Okay. I think I won't have enough time to cover the part with aggregations. So this is also very nice work by the dynamic Yamakakis algorithm. So I think I won't go through the algorithms here. The only thing I want to share with you is something like, how does the aggregation increase the hardness? Okay. Previously, we considered that if we have insertion-only update sequence, then all the frequentless query can be handled efficiently. But if we with aggregations, some queries cannot achieve a very efficient data structure. For example, this very simple query, it is frequentless, but with aggregations, we need root n update at the lower bound root n update time, and also for this query. Yeah.
For arbitrary aggregation or min versus sum, there should be a difference.
I think the lower bound, we only require the annotation to be just the one. You just do a sum and yeah, it's count. Yeah, exactly. It's already hard. Yeah. The proof is quite interesting. So in the previous one, we used the join condition to simulate deletion. But here we use aggregation to simulate deletion. Okay, let me show some.
Over the algorithm, I don't know.
Okay. Do I have time to do that?
So you have technically until roughly 11.
Oh yeah, yeah. I think I will upload the slides to Slack, and there are many animations there. I think just talk offline, yeah, about the algorithm. So how to use the aggregation to simulate the deletion? Here we still want to simulate the OMV conjecture. We use the R1 to encode the matrix, okay? We also use the R2 to encode the vectors here. And we let the W as the result vector for this query, and we know MV1I is 1 if W1I is greater than 0, okay? Then we encode the V2 by R2 again. But now we use their difference to simulate the result of MV2. Okay, so we don't have any deletion there, but we can use the difference between the aggregation to see the difference, to see the result of MV2. Okay. Yeah. Yeah. So similarly, we have only have a Boolean query. This is also hard and insertion only update sequence with if we just want to count. Okay, no count here. Just want to detect whether exists a result or not. And similarly, we use the OUMV. And here again, we use the aggregation to simulate the deletion and the insertion here. Yeah.
When you say aggregation, do you need like a specific semi-ring to do this simulation?
No, we just have you just count.
Like this is the summing of natural numbers?
Natural numbers, yeah.
I see.
So I will stop here and with a few interesting questions. So is the joint tree-based enclosure list good enough? And for if it's good, yeah, how about the enclosure list for aggregations, and how to handle more complicated update sequence, which is not the first in, first out, then have some other pattern or properties, and how to adaptively find a good generalized joint tree when you have more information about update sequence, and how to support more general queries. And I think Wolfgang have done some work for theta joins. And another one is how to do batch update, because we only talk about single update, okay, in the talk. When you have a batch update, so what's the whole picture? Yeah. At last is with self joins, how the lower bound will change. Yeah. Okay, so I will stop here, and I hope we will give you some idea for the discussion. Yeah. Thank you.
I think we can take a little break, like 15 minutes or so, and come back at 11 for the last discussion of this workshop.